Welcome back to ECE 220. We are now in Chapter 7. We have 3 more chapters to go for the semester. We have Chapter 7, which is first order circuits or RL-RC circuits. And then we have Chapter 8, which is second order circuits, where we have 2 energy storage devices. Typically, we will simply analyze RLC circuits that are either in series or parallel. And then Chapter 9 is when we get into sources that excite the system sinusoidally. Sinusoidal steady state analysis. And that's where we're using phasors, we're using complex numbers. In the follow-on class, in ECE 320, you will actually be using Laplace transforms to do some of this circuit analysis when your circuits become more complicated than second order. Well, you'll use Laplace for first order, second order, fifth order, etc. And then by doing Laplace, you've now converted into the frequency domain again, and you get to do algebra instead of differential equations. Today we're going to play with differential equations. We're not going to do Laplace transforms today. But some more announcements. Group A, you are going through lab number 3 this week. Tuesday is already, I hope, gone through successfully. We have Wednesday, Thursday, and Friday's labs these afternoons for Group A. Group B, your lab number 2 report, if you're in Section I, that's due tonight. And your pre-lab for lab number 3 is due on Saturday. If you missed the first minute or 2 of this discussion, we are now in Chapter 7, which is first order circuits. And today we're going to be talking about their natural response. When we're not exciting them with any external source, we may excite them to get initial conditions established, but now once we have initial conditions on these energy storage devices, we want to let them go and see how they behave. And giving you the, I guess, spoiler alert, these are all going to be exponentials. We're just exponentially decaying. How fast that exponential behaves is what you have to pay attention to. What is the exponent in this exponential decay? We'll look at the governing differential equations. Now that we have Eli and ice, we know that these energy storage devices of inductors and capacitors do store energy, and they give us this time rate of change behavior, this dV dt or di dt in the circuit, or those are in our current voltage relationships. We'll just start with one energy storage element in our device, an inductor or a capacitor, and that could be a couple of inductors in series or a couple of inductors in parallel. Those could be equivalently made into one inductor. You might have a circuit that has 2 inductors and you go, I can't analyze this. I only know how to solve first order circuits. Well, look around. Hopefully they can combine. If they can't, then we're into second or higher order circuits, and you have an excuse for not knowing how to solve that just yet. But there are many different applications, not just circuits, that can be modeled by these first order linear differential equations. So if you're not that excited about circuits, even though you're in this class, you can apply this these techniques to different systems, mechanical systems, thermal systems, etc. Knowing first order differential equations is important. We'll create a common structure, and then we really just have to solve it once. We'll just have to keep track of what tau is. This is the time constant that we will be referring to, and that time constant The name gives it away. It is a time. It is a length of time, and we'll be talking about how that length of time influences the exponential response. We'll solve first-order linear differential equations, and then we'll establish initial conditions by switching sources in and out of our circuit. What's happening before the switch? What happens after the switch? To start, let's look at a natural response. And here I'm saying there's no external source. You don't see a current source or a voltage source. If you see one, there's probably a switch present, and that switch will be open or closed to establish the initial current or voltage on the inductor or capacitor respectively, and then it will move to its new location once it's established the initial conditions, and you'll simply be faced with a circuit that looks like what's on the left, an RL circuit, or what's on the right, an RC circuit. And the key feature here is that single energy storage element in the individual circuits. So the key feature is one energy storage element in each circuit. When you see a circuit like this, you can go, oh, this is what we learned in 220, ECE 220. How many have already completed or are enrolled in differential equations? So you've seen this before. So today's class, you could be coming forward and presenting. Okay? Who wants to volunteer? Do we have any volunteers? I can remove the microphone quite easily. Let's find the governing differential equation. So, if you really didn't care for differential equations, hopefully after going through 220 you'll like them more. If you loved differential equations, hopefully you will still love them after going through 220. I hope to have the slope in a positive direction relative to differential equations after looking at them through the ECE 220 lens. All right, so now we're finding these governing differential equations, and this is why I'm stressing Eli and ice. Eli gives us the information we need about the current voltage relationship of an inductor, which is V sub L is equal to L di sub L dt. Seeing that allows us a lot of information. This di sub L dt is the important piece relative to an inductor. We're taking the time, we're interested in the time rate of change of the current through that inductor, so we're going to write equations in terms of that variable, in terms of I sub L of t. And you might hear this variable, I sub L, referred to as a state variable. If you know the state, if you know the value of that variable, then you can describe what else is going on in the rest of the system. If you know this, in subsequent classes, you might have 10 state variables. If you know all 10 variables, then you can say what's going on in the entire system, no matter what else is happening. Those give you the state, what's happening relative to the circuit or the system. So this di dt is now the derivative of a state variable, and when you see you have, or that you're dealing with inductors, what you immediately want to be thinking is, oh, inductor currents are important. They don't change instantaneously. They're continuous. So when you see an inductor, now you say, oh, I have an inductor present. Then you may want to be focusing on the current associated with that inductor. That's the state variable, so you might want to start writing your differential equations in terms of inductor currents. You hear inductor, think inductor current. And one thing to keep in mind is the current of inductors or maybe I should just say current of inductor remains continuous. For example, if we had some switch happening at time 0, we could still say that the time or the current of that inductor right before the switch happened, which we will label t of 0 minus, that's to the left of time 0. The current at that instant isn't going to change across 0 and on the other side of 0, which we call 0 plus. So we have a switch going on, but that inductor current is going to stay the same on either side of that switch's action. It's continuous. We have the same or a similar development relative to the capacitor. Ice tells us we now have I sub c is equal to c dv sub c dt. Now we know that we need to be focusing on the capacitor voltage if we're writing equations. In terms of capacitor variables, we want to focus on the capacitor voltage. Again, we have this derivative. And our state variable associated with a capacitor is its voltage. And the voltage of a capacitor remains continuous. As an example, V sub c of 0 minus will be the same as V sub c of 0 plus. And if you see capacitors in your circuit, then you want to be thinking voltages in terms of the variables of interest. And now I have to be probably a little bit careful with how I write my L's and the C's. That L is almost starting to look like a C a little bit, but that's an RL. This is a resistive inductor circuit. We now know to write that in terms of the inductor current. Which is I sub L of t. If we now have this circuit in front of us, and we want to write the equation in terms of I sub L, what kind of equation should we be writing? Kcl or Kvl? Any ideas? Kcl kind of is begging to be used because we said current, but now we want, if we think about what is happening, if we write things in terms of the current, then we have Ri is the voltage drop across that resistor, and we have L di dt. Both of those voltages are in terms of the current variable, and we can sum those up in a KVL and set those equal to 0. So in fact, if we are writing or trying to find the governing dynamical equation for this circuit, we actually are wanting to focus on a Kvl equation. And that will keep us then with our terms in that Kvl equation all containing the variable that we want, the state variable that we want, which is the inductor current. If we now write Kvl for this circuit, starting in the lower left, we have Ohm's law, which is R I sub L of t. That's the voltage drop from bottom to top. We're going in that direction. And then we have the voltage dropped across that inductor as defined by the current direction, or the reference current. That's now L di sub L dt, and that's equal to 0. If we're playing with differential equations, we probably want to start isolating the time rate of change variable. It's first order. We're just going to have one of those. Let's now put one of these on one side of the equality sign, and the other term let's keep where it is. Let's now say we have L di sub L dt is equal to minus R I sub L of t. And knowing that we want our equations to eventually look consistent in terms of structure, let's go ahead and divide both sides by the resistance R, the resistance value. Or we now have L over R di sub L dt is equal to minus I sub L of t. And if we really want to preserve the structure, let's just bury that inside another variable. Let's call that ratio of L over R, let's just call it tau. So now let's let tau equal L over R. And now that allows us to write tau di sub L dt is equal to minus I sub L of t. That is the differential equation. It's first order that governs the dynamic behavior of the current in that RL circuit. And we now are very comfortable, I hope, in deriving that relationship. We have tau. Now if it's just some generic variable, dx dt is equal to minus x, where x in this case is I sub L of t, the current in that inductor. What about the RC circuit? When I say capacitor, you say voltage. We have to go back to ice, don't we? So it's getting colder now. Now we think ice. So we now have, I say capacitor, you say voltage. So we're writing in terms of capacitor voltage, or V sub C of t. And now, what if we want to write the dynamic equation describing the behavior of that circuit, what would you guess we want to use now? KVL or KCl? Remember, inductors and capacitors are duals. So we've already used KVL for the inductor. What do you think we're going to use for the capacitor? its dual, which is Kcl. Let's now write a Kcl equation and try to now write that, or in so doing, and so writing that equation, hopefully we'll have an equation that's true, and it will be written in terms of this state variable, which is the capacitor voltage. If we're writing a Kcl equation, let's pick a node and let's just now say that this is our capacitor voltage referenced to that lower node. Now you can write Kcl. You know the current out of that node, the currents out of that node sum to 0. We have a current down through the resistor, which is V sub C of t over R. And we have a current down through that capacitor, which is given to us by ice, which is C dV sub C of t dt. And that's equal to 0. Now I'm curious, in your differential equations class, did they teach you circuits? I see some yeses, some nos. Or did they just say, oh, this happens in a circuit, and give you the equation? Did they get into KVL, KCL? No? Okay. Just curious. So now don't tell them we're doing differential equations in here, but we are. All right, so now let's manipulate this, move this around a little bit. The last time we said, oh, let's isolate the derivative term on one side. We can keep a minus some state variable on the other side by multiplying now both sides by R, and we now have RC dV sub C dt is equal to minus V sub C of t. And again, if we let tau be RC, now we can write this as tau dV sub C dt is equal to minus V sub C of t. And we have another equation that structurally looks exactly like what we just had for the inductor. Now our time constant is different, tau is different, but the structure is tau dx dt is equal to minus x, where x in this case is the state variable associated with the capacitor, which is its voltage. That should be structurally consistent with the inductor first order differential equation. Now I don't want you to leave class thinking that, oh, we have a first order differential equations and they only appear in circuits. No. You can have car velocity. If you wanted to know the dynamic behavior of the velocity of the car, if you wanted to model the rotational spin of a DC motor, you could describe that by a first order differential equation. You could have a thermal system, which might be a room, it might be an oven, something. You can now describe that by a first order differential equation if it's not that complicated. Obviously now you need what? One energy storage element and only one. A fluid system, radioactive decay, all of those can be modeled with a first order differential equation. So don't just think that this stuff that we're talking about today is only applicable to circuits. Now you can be in a room with other engineers, other scientists, and they can be talking about some dynamical system, and you'll go, that's behaving similarly to what I'm used to, or that's behaving a little differently than what I was expecting. But you now have some intuition based on your circuit experience, which we're developing now. Here's the note. Both of those circuits that we just looked at, the RL circuit and the RC circuit, we were able to give them the same structure by simply defining a product of variables or a quotient of variables with this parameter tau. And that tau is in fact a time constant, and it has units of time. And how did we define those? Well, for the RL, we said tau was L over R. Now somebody says, what's the time constant of your circuit? You can boil it all down and say, oh, I have an equivalent resistor and I have an equivalent inductor. I take L over R. That's the time constant of that circuit. Likewise for the capacitor circuit, you now just take the product of the resistor and the capacitor, and that now is your time constant. And where's that coming from? Well, we can think this through in unit terms and say, why do these products and quotients give us time? Why are they called a time constant? Ohm's law, V is equal to Ri, so we can solve for R. That's in both of these expressions for the time constants. That's volts over current, V over I, if we solve for R. Eli, that tells us now that we have V is equal to L di dt. Or if we solve now for L, that now says that we have V over di dt, and in unit terms, this is volts over I over, let's just say, seconds for our dt. So this is now, what are the units on L? V over I over S. Those are the units on L. If we now put those units into this expression for L over R, what happens? Well, now we have V over I over S. That's why I don't do S's. Let me do a script S over R, which is V over I. That's in the numerator of the numerator, and this is in the numerator of the denominator. Those V's cancel. The I's cancel. And the S, if we multiplied by 1, hopefully that sort of gives you a sense of why we're saying tau equal to L over R is a time constant. It has units of seconds. So now when somebody says, oh, what's the time constant? And they say, oh, it's L over R, you go, okay, that's a time. What is that time? What's the length? Ice, we can now use to help us find the units on the RC time constant and verify that it's seconds. So ice says we have I is equal to C dV dt, or C is now I over dV dt, which in units give us I over V over S. And R we started with Ohm's law, that was V over I. We multiply that by C, which is I over V over S. We do the appropriate cancellations, and we're left with S, or seconds, for the units on RC. So when we say a time constant of RC or L over R, hopefully now you are okay with calling that a time constant. It has units of seconds or units of time. We'll be back. So tau will be back. We'll work with tau in a little bit, but now let's start solving these differential equations. With respect to the RL circuit, We wrote a KVL just as a reminder. We isolated the derivative and we put a coefficient in front of it, L over R. We defined that to be tau, and we said, oh, this is tau times the derivative of I is equal to minus I. What function is the same before and after differentiation? What f of t is equal to its derivative? E to the x, right? So now if we look at, if we now said, oh, suppose I, did we call it L? I sub L of t is equal to e to the x. Or, where did x come from? I sub L is in t, so let's just call it e of t. Then if we differentiate that, that's e of t. That's kind of what we want, but now if we look at ours, we had a negative sign in there. But we can fix that. What about using e to the minus t? Now if we differentiate that, that's even better. So now what we've seen is for this structure, tau dx dt is equal to minus x, we're expecting a solution for x to be exponential. So our exponential structure is what we're anticipating. Exponential structure of the solution to this homogeneous equation. Homogeneous means it's the same. We have an I on the left, we have an I on the right of that differential equation. We don't have any other structure of a function present. We just have I sub L. So we're expecting that I sub L to have an exponential structure. So now let's get back to the solution of that differential equation, which was tau di sub L dt is equal to minus I sub L. And you can use your favorite strategy. Let's just use separation of variables. Let's separate or rearrange this equation such that we have one variable on one side and another variable on the other. I sub L on one side and time on the other. So let's now separate our variables. And we now have di sub L I sub L over I sub L is equal to minus 1 over tau dt. Now we have one variable on one side, another variable on the other. We've got them separated. We can integrate both sides now that they're by themselves. So let's now integrate. And just to keep things a little bit clear, because I want my limits to be in terms of time t, I'm going to let my variable of integration on the right, instead of dt, I'm just going to call it dx. Is that okay? So now I'm going to integrate, but on the right I'm going to replace dt with dx. My limits will be still in terms of time. If we now integrate both sides, we're now integrating from t0, some initial time, to some final time. di sub L over I sub L is equal to, And the 1 over tau, that's a constant. We'll just pull that out in front of the integral dx from t sub 0 to t. What's the integral of dx over x? Do we remember? Where's my table? That's ln of x, right? The natural log of x. So, or here it's I. So we have natural log of I sub L from t sub 0 to t is equal to minus 1 over tau x from t sub 0 to t. Let's now evaluate that at the upper and lower limits. We now have ln of I sub L of t minus ln of I sub L of t sub 0 is equal to minus 1 over tau t minus t sub 0. And for now, let's just not worry so much about the initial time. Let's just let it be 0. So now we're going to go ahead and, for now, let our initial time be 0. Or we now have, and is it okay if I use a property of logs? If I'm subtracting logs, I can combine their arguments into a division, or I now have natural log of the quotient of I sub L of t over I sub L of 0. That's just a property of the logarithm. And I've now set t sub 0 equal to 0, so I now have just t over tau with that minus sign in front. I'm trying to solve for the current in that inductor. I now need to isolate or pull I sub L of t out. If I can now take the anti-log of the log, it's going to pop out for me. Let me now take the anti-log of both sides and I now end up with this I sub L of t over I sub L of 0 is equal to e to the minus t over tau, where e is now our anti-log function. And we can now multiply both sides through by I sub L of 0, and we have I sub L of t is equal to our initial current through that inductor, e to the minus t over tau, and that's true for t greater than or equal to 0 since we assumed t sub 0 was 0. And now what do you see when you see that expression? If you now wanted to sketch I sub L of t, what would it look like? That's just the exponential decay. And what's our initial value of the current? What is I sub L of t when t is equal to 0? We replace t with 0, e to the 0 is 1, and we get what we said we were supposed to get, which is the initial value of our current, I sub L of 0. Let's now just say that that's right here. This is now I sub L of 0, and now we have this exponential shape. Theoretically, do we ever get to 0? No, but practically we get there pretty fast. We are going to sort of block this waveform into one period that we will call the transient interval, and then we have this second interval where it's effectively at 0, and that's its steady state value. And it's helpful to actually understand what this looks like, or how this behaves relative to the only variable in that function is time, little t. And the exponent is a function of time and tau. So if we know tau, then we can compare that with little t and say how many taus are we away from 0. If we are 1 tau away, and that's called one time step or one time constant into that functional expression, what's the value of I sub L of t? So let's now just sort of create our own table. Let's look at what this current does in multiples of our time constant tau. And we'll begin really difficult. Let's say that t is equal to 0 tau. Then we know that I sub L of 0 is I sub L of 0 e to the minus 0 over tau, which is where we started. That's what we expected. Now, what happens when we look at one time constant, when t is equal to tau? Now we have I sub L at time tau, and that's going to depend on our time constant, L over R or RC. Let's say it's 100 milliseconds, or it's 0.1 seconds. So now we want I sub L at 0.1. We now say, oh, that's I sub L of 0 e to the minus tau over tau. But that's now just scaling the initial value of our current by e to the minus 1. And what is e to the minus 1? Do you remember? We've talked about it already in class, haven't we? If we really plugged it in, would it be 0.36? I wrote it down. 7, let's say 8, but we typically, and if we just keep going, 3.6788, we typically just approximate that to be 0.37. Or now we're 37% down from where we started, and you can kind of visualize that. So if you went back to your plot, here you could now mark this off and be a little bit more accurate, and you could say, oh, by the time that we get to 37%, oh, and this is a terrible drawing, that's now tau. That's where we are in terms of time interval. We're one time constant away from where we started at time 0. We're 37% of where we were beginning. Now if we say, well, what happens when we're at 2 time constants into the expression or into this functional curve? We now have I sub L of 2 tau, which is I sub L of 0 e to the minus 2 tau over tau, or I sub L of 0 e to the minus 2. That's where these 2 time constants, 3 time constants, when your exponential is written as e to the minus t over tau, all of these 1 time constant, 2 time constants, 3 become e to the minus 1, e to the minus 2, e to the minus 3. E to the minus 2 is 0.135. So this is now 0.135 e to I sub L of 0. So we're down at 14% of where we started in two time constants. I sub L of 0.2, if our time constant was 0.1, we're almost at the end. We're 14% of where we started. What about at three time constants? This is now e to the minus 3 I sub L of 0. And did I compute that? This is now 0.0498. So we're at 5% of where we started after three time constants. The next two time constant values are used a lot in subsequent classes. You might hear about a 2% settling time. That's given by four time constants. So now you say, oh, what's your time constant? Oh, in four time constants, you're within 2% of where you started. I sub L of 4 tau, e to the minus 4 is 0.0183, but we just refer to that as 2%. Do you see that's close enough? So now we're within 2% of where we, or 2% of what we were at when we began. Now at 5 time constants, we're at the 1% mark. And this actually is a little bit less than 1%. It's 0.0067 I sub L, but it's generically referred to as the 1% settling time. That's why we say, oh, in 5 time constants, we've reached infinity. Why? Because we're less than 1% of where we started, and that's close enough. So now when somebody says, oh, what's happening at infinity? All you have to do is move 5 time constants out into your functional form and say, we're there. So that would be half a second if our time constant was 0.1. In half a second is all we would have to wait. So when we get into chapter 9, we don't have to wait very long to get into sinusoidal steady state. We don't have to wait a month or two. We just excite our system, wait 5 time constants, and then everything is shaking at the sinusoidal frequency that we excited our circuit with. Takes 5 time constants. It's not very long when you're dealing with electrical circuits or electrical systems. Well, now how are we going to solve this? We have an idea. Well, we've already found the solution. It's I sub L of t is I sub L of 0 e to the minus t over tau. All you have to give me is RC and the initial current. And then I have your homogeneous solution available to you in this structure. How do we establish initial conditions? Well, we do it by switches. It's not magic so much. We don't bend down and then put it on the table and say, there you go. But we might, on an exam, we might say, here's your initial condition and give it to you. But let's say that we now had this circuit. And look at the polarity labels. It's upside down, but that's intentional. And just so we don't have sparks, I'm trying to do this make before break switching behavior. And let's just assume that this happens at 0. Here is, let's say, our source resistance. Here's L, and here's our R. Do you see we really have 2 different time intervals that we are interested in the behavior of this circuit? We analyze it for t less than 0 and what do we have? We have the circuit on the left. And if that source has been present for a long time, which it has been, what's that inductor look like prior to t equal to 0? It's a short. So our first one, we look at t less than 0, and we really just have this. And that gives us I before t equals 0. And then we look at t bigger than 0, and now we have this. And what's that I? This I at 0 minus is in fact V sub s over R sub s, and we might just call that I sub s. And what do we know about the current on an inductor? It's continuous, so now we know at time 0 plus, this is going to be the same as what it was at 0 minus. Now we've established the initial condition on that inductor, and we can solve that differential equation given that switched source to establish the initial condition. We'll pick up there tomorrow.